Hello and welcome. In this video, we will be looking at graph theory as it relates to computer science. We'll start by looking at a simple definition of a graph. A graph is a collection of vertices and edges, all right? So a graph is made up of a set of vertices and edges as indicated on the screen here. Each point on the graph is referred to as a vertex, all right? While the line that connects the different vertices together form the edges, all right? So here we have an edge between vertex V and W, and this edge is called E, all right? Another edge that we have is the line that connects X to U, right? So you have different edges. So in a given graph, you'll find different sets of vertices and edges. All right, so in this scenario, here we have them listed here. The vertices are S, U, V, W, X, Y, Z, while the edges, as indicated earlier, are the lines that connect the different vertices together. So we have a edge XS here, XS. We have another edge XV, that is X to V up here, and so forth. All right, so you can look through the graph to see the different edges. So normally, an edge is labeled as indicated here. So we may have an edge, say the edge VW, being labeled probably E or whatever name you want to give to it. A vertex you may find in a given graph that you have some vertex that are said to be isolated because they're not connected to any other vertex. Just like in Jamaica, we have some pieces of lands, like the Goat Island, that is not connected to the mainland. Right, so we have some vertices that are isolated. So we call those isolated vertex. We also have parallel edge, and an edge is said to be parallel if it runs alongside another edge. So for example, here we have the edge AB, and we have another edge here, AB, that runs alongside AB. All right, you can think of it as a two-way lane on the road or on the highway. And then we have loop, and a loop is just an edge that starts at this and ends at the same vertex, like here. So this edge starts here, goes around here, and it ends here. All right. So any edge that starts and ends at the same point forms a loop. All right. There are other instances where we have like a path that starts, say, at C and ends at C. So we could go from C to D to E back to C. That is also a loop. All right. So a loop is just an edge that starts and ends at the same vertex. All right. And you may have a loop that includes more than one edge. All right, as indicated earlier. So we may have C, D, E, C. All right, that will be a loop. The important thing is that it starts and ends at the same location. All right. So we have simple graphs like these, as indicated here. A simple graph is just a graph that doesn't have a loop. A graph without a loop or any parallel edge is said to be a simple graph. All right. So here we have a graph with vertex 5, vertex 1, vertex 2, vertex 3, vertex 4. It's a simple graph. It has no parallel edges nor any loop. And then we have a weighted graph. A weighted graph is a graph that has a number on each edge. And this number could represent different things. It could represent the time it takes to move from one vertex to another. Or it could be the distance between the one vertex and another vertex. It all depends on how you, what you're representing. All right. Then we have the direct graph, and the direct graph is just like the simple graph, except that it has no an arrow that indicate the direction in which data ought to flow throughout this graph. All right, so in this case, we know that we have a path A to B, but we do not have a path from B to A. As you can see, there is no arrow pointing back from B to A. So this would be like a one-way street. Again, down here, we can't move from B to C, but we can move from C to B, all right, based on the arrow. So the arrow tells us the direction that we can move in on the direct graph. So very important, so make note of that, all right? And then we have other graph. We have like a complete graph, and with a complete graph, if you are familiar with the mesh networking computing, you find that each edge is connected to the other in the complete graph. So edge E is connected to all the other, vertex E, sorry, is connected to all the other vertex in the graph. All right, so all the vertices are connected to each other. So E is connected to A, E is connected to B, E is connected to C, and D, and that goes for all the vertices. All right. All right, good. So we're going to look at how we may go about creating a very simple graph for a shopping mall. So we're going to just open up here. All right, so here we have a shopping mall, and let's see if we could create a graph to represent what is here. All right, so we're going to use each store on the shopping mall as a vertex. So let's give this store some name. All right, so this looks like a bank. So let's call this bank. Let's call this pharmacy. All right, let's call this bookstore. Let's call this, let's call this burger. Burger Queen. This looks like what? We have some bags. We have, looks like an attaché. This is probably some office. All right, let's call this a lawyer office. Perhaps a lawyer office. Let's call this a dentist. All right, this looks like, all right, so I'm seeing here, this looks like a stove. All right, and this is like a kitchen. All right, so let's call this kitchen. All right, so over here, we have some mobile service. And here we have something that looks like a library or a bookstore. All right. All right, so that's book. Let's call this one a library. All right. So we are going to look, I'm going to call this part the main office. So we're going to use the different stores to represent the different vertices on this graph. All right, and we're going to draw a simple graph as well as a direct graph. All right, so we're going to start. So we're going to just use some circles to represent each vertex. All right, and I'm going to use the first, use a letter R2 to name each vertex. So this one is the bank. Then you have the library here. Then you have the mobile here. Then you have the kitchen. Then we have the dental service. Our lawyer. We have burger. We have the bookstore. pharmacy to the main office. All right. So let me just label them. So this is bank. Use B for bank, L for library, M for the mobile, K for the kitchen, D for dentist, LW for lawyer, BQ for Burger Queen. So we get our burger. BS a bookstore. Use P for pharmacy. And for the main, we're gonna use MN. All right. So if we're doing a simple graph, all we would do is just show how these are connected. All right. So is there a path? So all I need to do is check to see if there's an edge between. Is there an edge between the bookstore and the pharmacy? Yes, there's an edge. So we just draw our edge. All right. Is there an edge between the, sorry, this is the bank and the pharmacy. Yes, there's an edge. Is there an edge now between the bank and the main? Yes, there's an edge. So we just draw our edge. Is there an edge? Just look, so you can look at the diagram. And if this was like an actual mall, think about it. Can you walk? So let's say these white lines represent the roadways, the path that you can take to move from one place to the other. All right, so can we walk from the library directly to the bank? Based on what is here, there's no line that connects the library directly to the bank. So can we move from the library to the main? Yes, we can move from the library to the main. All right, can we move from the library to the mobile? Yes, there's a path there, the line connects. So the library can be connected to the main, to the mobile rather, the library to the mobile. Can we move from the mobile to the main? Yes. So the mobile can go to the main. Can we move from the mobile to the kitchen? No, there's no path from the mobile to the kitchen. And we can move from the kitchen to the main. So just draw a line there. All right, can we move from the kitchen to the dentist? Yes, there's a path there. All right. Can we move from the dentist to the main? Yes, we can. So we could move here and go to the main. So there's a path between the dentist and the main. Can we move from the lawyer to the main? Yes, we can. Can we move from the lawyer to Burger Queen? Yes, we can. So just draw the lines to connect them. Can we move from the lawyer to the main? We have done that. Can we move from Burger Queen to the main? Yes, based on the line. Yes, we can do that. So there's a path here. Can we move from the bookstore to the main? Yes. What about from the bookstore to Burger? Yes, there's actually an edge that connects the bookstore to Burger. So we can go directly like that. We are now at pharmacy. So you can move from the pharmacy to the main, just like that. All right, so that's a simple graph. All right, so that is what a simple graph would look like. All right, now we could make this a weighted graph. That is, if you want to show the amount of meters between the different stores, or if it's a case, the distance is far, like the amount of kilometers between different stores, you could write that on the line. All right. Also, if it's a case where we have like a one-way street, let's say, for example, we can walk from the library. It's okay to walk from the library. Oh, this one is what? Library, yeah. It's okay to walk from the library to the mobile. So let's say, or if we are driving, for example, this could be a driving map. So there may be a path going this way from the library to the main, but maybe you don't have a path going back, right? So it therefore means that if you want to go back to the library, you may have to go to the main and next to come back this way around. So there could be a one-way street here. So this would make it into a direct graph. All right. So the arrows, by adding the arrows, it now move from a simple graph to a direct graph. All right. Also, so we could have a part like this. So from the main to the library, to the mobile, back to the main, and then we could have a path now from here to the kitchen. All right, so we could have a two-way street from the kitchen to the main. So let's put that in. So to capture that, we'll just show that we can go this way and can also go this way. All right, so that indicates that it's a two-way street. So we can move in either directions. That means if you move from the main to the kitchen, you can move directly back. All right. If you're moving from the kitchen to the dentist, let's say there's just a one-way street there. So you just put an arrow and that shows that it's a one-way. So in order for you to, if you move from the kitchen to the dentist, if you want to get back to the kitchen, perhaps you'd have to go back to the main like that. All right, so you'd have to go around here. All right. And then now, so depends on what we are representing. We can set it up in different ways. All right. So again, if there's a path between the pharmacy, so again, maybe from the pharmacy to the main, we may want to have a two-way street. From the pharmacy to the bank, there could also be a two-way street, so as to minimize the time. I could even have a two-way street here, two-way street here. All right. And maybe we can set it up so that from the main to the bookstore is a one-way to Burger King, Queen. So we can have two ways movement to the food places. All right. So like that. That's a two-way street. So that's a direct graph that we have created there. All right. So each line should have an arrow that indicates the direction of flow. All right. So we can move from the main to the lawyer office, and we can also move back. Right, so we'll have to capture that there. And of course, we could have a two-way street here. All right. So there are different scenarios, and based on what you're capturing, it may vary. Again, if you want to show like distance, probably how long it would take you to move from one point to the other. So how long would it take you to move from kitchen to the dentist? If we want to capture that, we could just put on the number on the line to show whether this is, say, 2 meters. Right? This would now make it not just a direct graph, but a direct weighted graph. So it would be a weighted graph now because it has a number on its edge, right? So if we have 2 there to represent 2 meters, and probably from here to here is 3 meters. Here is probably 5 meters from here to here. All right, so this would make it now into a weighted graph. 3 meters there and so on. Or kilometer, depend whichever unit we're using. All right, so we can just indicate that. All right, so if each line has a weight on it, it turns it into a weighted graph, and not just a weighted graph in this case, but it's a weighted direct graph. So that's pretty much how we go about constructing a graph. All right, so we have different types of graph, and that's how we'd go about constructing them. All right, so the next thing that we need to know about is the degree of the vertex, or each vertex in a graph. Now the degree of the vertex is just a count of the amount of edges that leaves are incident on the vertex. So like in this case, just count how many lines leave each of the vertex. So let's look at C. look how many lines enter or leave C. So you have one line here, 2, 3, 4. So the degree of vertex C is 4 because we have 4 lines leaving it. All right. So you have 1, 2, 3, 4. Vertex A. Let's count how many lines incident on A. That's 1, 2, 3, 4. So the degree of A is 4 as well. All right. Let's count how many lines incident on B. So you have 1, 2, 3. So the degree of vertex B is 3. All right. Same thing for E. Count how many lines incident on E. You have 1, 2, 3, 4. So the degree of E is 4. All right, let's check G. For G, you have 3. So 3 edges incident on G. So the degree of G is 3. And you can work out the others and see. All right. Now, a graph, the degree of the vertex can help us to solve a number of problems, one of which I will highlight. So depending on the degree of the vertex on the graphs, if all the vertices on the graph, if all the degrees of the vertices are even, right? So if they're all even, then the graph is said to be a Euler graph because it has a Euler cycle. All right. So a Euler cycle in a graph is just a simple path that passes through every edge of the graph only once. So if we can visit all the vertices of the graph by passing through all the edges just once, then the graph is said to be a Euler graph. So let's look at an example. All right, so I want to draw a Euler graph. So here's vertex A. To B. To C. So all we have to do is make sure that each of the edge has an even degree. Each of the vertex has an even degree. All right, so far all of those are even. Let me just add some more lines to the mix. So these are no longer even. Those are odd. This one is even, this one is even. All right, so I'm gonna add one more. G. All right, so this is now even. This 3. This one is gonna make it 4. All right, so this is even. So this is 2. 2 is an even number. 1, 2, 3, 4. This is an even number. 2, 3, 4 is an even number. 4 is an even number. So let's just write out the degrees. So the degree of G is 2. That's an even number. The degree of A is 4, which is an even number. The degree of B is equal to 4, which is also an even number. Degree of E is 4, which is an even number. Degree of F is 2, which is an even number. Degree of C is equal to 2, which is an even number. So if you're given a graph and you're asked to check to see if the graph has a Euler cycle, all that you need to do is to just check to see if each vertex on the graph has an even degree. And we can do this by simple checking the degree of each vertex. So let's see if if this actually has an even degree. So let's see if we can visit each of the vertex on the graph by passing through the edges once. So we are not supposed to pass through any edge more than one time. So we can start at any location. So let's see if we can actually do this for this graph. So let's start, for example, at F. So the aim is to pass through to visit all the edges all the vertices without passing through any edge more than once. So let's say we start here, we could move up here. That would take us to A. So from A, we could go all the way over to G. All right, so we can visit all of them, and we're not gonna repeat any of the edge. So we could come over to B. All right, so from B, we could come over to A. So we're not gonna go through any edge more than one time. All right. And from A, we can go down to E. All right. And from E, we can go up to B. From B, we could come down to C. And from C, we could go to E. And then we could just go back to F. All right, so we end up where we started. So this is just proof that this graph has a Euler cycle. And without doing the manual trace that some persons may not necessarily like to do, all you need to do is just to check the degree of each of the vertices. And once each of them is even, then you can conclude that the graph has a Euler cycle. All right. So thank you for watching.